Friends, let us continue to derive the stiffness coefficients of Triceratop. We discussed the last lecture the stiffness coefficients till roll degree of freedom of the buoyant leg. Now, we will start discussing the stiffness coefficients from the pitch degree of freedom of the buoyant leg. So, just for recollection, you know Triceratop has 9 degrees of freedom. There are 6 degrees of freedom of the buoyant leg as you see here, and 3 degrees of freedom for the deck, numbered sequentially as 1 to 6 for the buoyant legs, and 7, 8, 9 are independent rotations of the deck which are not connected and transferred from that of the buoyant leg. That happens because of the presence of ball joint. So, the dimensional variations are given in the figure as shown on the screen now. The degrees of freedom are anyway marked. So, we are getting 3 degrees of freedom for the deck and 6 independent degrees of freedom for the buoyant leg, which makes it 9, and we now understand that my stiffness and mass matrices will be of size 9 by 9. Let us continue to discuss the derivation of stiffness coefficients from the first principles from the pitch degree of freedom. Let us say this is my deck, I have ball joint, which is now connected to the buoyant legs. Which are anchored to the seabed using high initial tension tethers similar to that of a tension leg platform. Being a triangular geometry, CG will be shifted towards the left side. Let us draw this line as my CG line. So, let us mark the degrees of freedom. This is my water line. This is my center of buoyancy and center of gravity. Let us say this is my CG point, where my degrees of freedom are marked as K 15 and K 35 and K 55. Center of buoyancy is located slightly in the offset because of a simple reason, you are giving pitch is a rotational degree. Therefore, there may be a possibility of a small shift in the center of buoyancy. So, the shift between these two is eccentricity, which we call as E phi, and change in tension because of the shift will be indicated as T 0 plus delta T phi. So, from this distance, this place or this leg P b by 3 and 2/3, where of course, this distance is P b in the plan dimension. The deck will have an independent rotation component, which will be K 85. So, now referring to this figure, so let unit rotation be applied in pitch degree of freedom of the buoyant leg. So, K 15 is given by T 0 plus delta T phi. There are 3 such legs divided by sum of root of squares of S u d square plus L square, where I will call this equation as let us say start with the new number here 1, where SUD is HCG minus H bar of sin theta phi. K2 phi will be 0 because no sway response in the buoyant leg due to unit pitch rotation of the buoyant leg. Delta T phi is given by 2 by 3 P b cos theta phi of theta phi of A e by L, because we are looking for an axial stiffness, minus 2 A e by. You can see here there are two legs which are closer to 1/3. So, I should say 2 A e by L P b by 3 cos theta phi of theta phi. So, equation 3 will give me the change in tether tension caused because of unit rotation in the pitch degree of freedom. So, K 3 phi Z b will be given by 2 0 plus delta T phi of cos theta phi 2 such legs plus T 0 plus delta T phi of one more additional leg separately, because in this figure 2 legs are oriented on the same line, whereas one leg is separate. So, I am writing it separately here, minus 3 T 0, that is the initial tension of the cable. Let us equation number 4. K phi phi theta phi will be now equal to F b into E phi plus T 0 plus delta T phi of twice of S 1 minus E phi minus T 0 plus delta T phi separate leg, which is S 2 plus E phi minus W deck of S u d, where E phi is actually H bar sin theta phi and S 1 is actually P b by 3 plus E phi and S 2 is P b minus S 1. Equation number 6. K 4 phi will be 0, that is rotation in roll degree of freedom due to unit pitch rotation is 0, because anyway roll and pitch are not directly coupled of the buoyant leg. Okay. These are all for the buoyant leg. K 6 phi is 0 because no yaw motion in the buoyant leg due to unit pitch rotation in the buoyant leg. K 7 phi is also 0 because no motion about sway axis of the deck, because we are talking about degree of freedom 7 due to unit pitch rotation of the buoyant leg. K 8 phi will be having some value, because this will have influence on rotation about surge axis. due to unit pitch rotation of the buoyant leg. One may ask me a question, how rotation from the buoyant leg is transferred to the deck? It is not transferred actually. When, look at this figure, when the deck is rotated, because of submergence happening between the legs, there is no transfer of this rotation from the leg to the deck, but deck alone will have some influence of variable tension which will make the deck to rotate. You please understand, variable tension imposes heave difference. So, variable tension imposes differential heave, and this is transferred from the leg to the deck, and that causes K85. So, K85 into theta phi will be essentially arising from K theta phi ZB SUD plus K1 phi SUD HCG minus H bar. Call C question number 7. So, now from this equation you can say Z top will be actually H minus H bar of SUD by tan theta phi, and Z bottom is H bar minus E phi by tan theta phi, which is equation 9, and theta 8 phi is actually tan inverse of Z top by P b by 3, which is one of the planned dimensions of the platform. Further, K 9 phi is 0, that is no yaw motion in the deck due to unit pitch in the legs. Okay. So, by this logic I have worked out K 1 phi, K 2 phi, K 3 phi, K 4 phi, K 5 phi, K 6 phi, 7 phi, 8 phi and 9 phi. So, I got all the 9 coefficients, 6 for the legs and 3 for the deck for unit rotation in the pitch degree of freedom. So, we derived now the 5th column of this stiffness matrix. So, let us now do the same for unit rotation in yard degree of freedom of the buoyant leg, that is theta 6 is given to be unity. Okay. That is why I want to do this. Let us draw the figure. This is my initial configuration of the platform. It is having a triangular deck. There are 3 legs, 1, 2 and 3. I name them as 1, 2 and 3. Let us now draw the new position by rotating it. Let us say I rotate by some angle at the CG. at the CG. Okay. We know this is PL and this is PB. Equation will be now available for deriving the stiffness matrix coefficients. Let us say this is my new position of the first leg. Let us call this leg as 3 and this leg as 2. Okay. So, the new legs 1, 3 and 2. So, now they will have new tension which is T 0 plus delta T 6, T 0 plus delta T 6 and T 0 plus delta T 6. Now, K 16, let us say now what are the degrees of freedom we are going to mark? We are imposing theta 6 unit rotation. So, we will get K 66 and further things. So, let us say K 16 is 0, that is no surge force due to unit yaw rotation of the buoyant leg. K 26 is also 0. So, we should say no sway force in the buoyant leg due to unit yaw rotation of the leg. So, by giving unit rotation, that is, let us impose unit theta 6 to the legs. Now, from the geometry we can say that A square and B square can be two new variables which can be P L by 2 the whole square plus P B by 3 the whole square and L 6 the new length of the tether because of this twist will be root of sum of squares of L square plus 2 A theta 6 the whole square. I call equation number 11. So, change in initial pretension in each leg is given by delta T 6 which is L 6 minus L of A E by L, equation number 12. Let us now summarize the force in heap degree of freedom. So, K 36 of L 6 minus L will be actually equal to or will be balanced by T 0 plus delta T 6 minus T 0 of that of 3 legs, equation 13. K 46 will be 0, that is no roll due to unit yaw rotation of the leg. K 56 will also be 0, that is no pitch due to unit yaw rotation of the leg